Hello, welcome to Physics 2, Lecture 25.5, Lenz's Law. So, as a bit of a recap again, recall that current is induced in a loop of wire if and only if the amount of magnetic field is changing. In other words, if the magnetic flux through the loop changes. Lenz's law basically is an addition to this. We now know that we might have an induced current in a loop, but we haven't figured out which direction it's going to flow. And doing so is actually not that simple. What I'm going to give you is the technical definition of Lenz's law, but then we'll kind of unpack it and give ourselves a guideline and set of steps on how to follow this process. So Lenz's law is a rule that allows us to determine the direction of that induced current. Lenz's law states the following. There is an induced current in a closed conducting loop if and only if the magnetic flux through the loop is changing. That's what we've already stated. The direction of the induced current is such that the induced magnetic field opposes the change in the flux. Now that is a lot to take in for one sentence. So again, we will spend time unpacking this for the rest of the lecture. I'll repeat it though. The direction of the induced current is such that the induced magnetic field opposes the change in flux. So what the heck does that all mean? Well, first of all, let's recap again. Magnetic flux can change in one of three ways. The equation that we came up with last time was AB cosine theta. So those three things can change. Either the field strength changes, so you can have a greater field strength or a weaker one. The loop can change in its area. So in that case, the area A is given by length times width, or pi r squared, what have you. So if you change the size of that loop, that will change your flux. We also took a look at what happens if you change the angle by changing the effective area of your loop. And one that we haven't necessarily discussed quite as much, but this goes along with the first point, the loop moves into or out of a magnetic field. So obviously you could keep the loop the same size, you could keep the angle the same, and the field strength could be the same. But if you have it in a region of no magnetic field, and then you slide it over into one that has magnetic field, you are changing the magnetic field inside the loop. So all of those things matter. Now, if the flux through the loop does change, we know again that a current is induced in that loop. So here's the key. That current generates its own magnetic field. Right? Because we know now that currents produce magnetic fields. It is this induced field that will oppose the change in flux. So, let's look at a few visual examples, and then we'll summarize with a guide on how to use this Lenz's law. So, we're going to go through three examples here. All of them include this situation. You have a bar magnet and a loop of wire with a meter on the side to detect if there is any current. So in our first example, we have the most simple, straightforward setup. You have a bar magnet with the loop of wire, and you're not moving any of them. You're not tilting the bar magnet, you're not moving it around, it's just completely at rest. And so even though it is producing a magnetic field, the flux or the change is zero. There is no change in the field through this loop if nothing is moving. So although there is a magnetic field present, there is no change, so there is no current. Okay, so it's all about a change. So let's make that happen now. Let's look at what happens if we change. Now this is going to take a while to go through. In this case, let's start taking that magnet and moving it downward. So if we're moving the magnet downward, it's moving closer to the loop. Recall that the closer you get to the poles of a magnet, the stronger the field is. So, as we move the magnet downward, we are increasing the flux through the loop because the field strength is getting stronger and stronger. So we have a downward magnetic field that is getting stronger. By definition, the induced current produces its own field that will oppose that change. So we have to oppose an increasing magnetic field. How do we do that? Generate a magnetic field in the opposite direction. You want to overcome a strengthening field, so make one in the opposite direction to weaken it. That means we have a field, an induced field, pointing upward through the loop. And by the right-hand rule, our first right-hand rule, if your fingers are curling up inside the loop, your thumb should be pointing in a counterclockwise direction around that loop. That is Lenz's law, and it's a lot. So let me run through it one more time. We are moving a magnet closer to the loop. Because of that, we are increasing the field strength. In other words, we are increasing the flux through the loop. The induced current that's going to be generated in the wire has to oppose that change. So it produces a magnetic field in the opposite direction to oppose that increase. That is the upward direction. And by the right-hand rule, if you have a magnetic field pointing upward, your thumb points counterclockwise around the loop. Let's do one more. It's the same situation, except this time we're taking the bar magnet and moving it further away. As we move the magnet further away, we are decreasing the field strength in the loop. In other words, the flux is decreasing. If we want to oppose a decrease, well then we want to make a field in the same direction to enhance it, to make it stronger, oppose that decrease. So in this case, you're going to get a magnetic field that actually points with the original one downward through the loop. By the right-hand rule, if you have a field pointing downward, your thumb will point in a clockwise direction. And so we know the direction of current in the loop as a result. One more time. You are moving the bar magnet away. That's weakening the field in the loop. In other words, that is decreasing your flux. To oppose a decrease, you want to enhance it by adding a magnetic field in the same direction. So it also points downward, and thus by the right-hand rule, you get a current in the clockwise direction. So let's go through a step-by-step list on how to follow Lenz's law. First, determine the direction of the applied magnetic field passing through the loop. So in these examples, the applied field was pointing downward, that of the north pole of the magnet. So determine the direction of the applied magnetic field. In that case, it was downward. Step 2. Determine how the flux is changing. In other words, ask yourself, is it doing one of three things? Is it increasing? Is it decreasing? Or is it steady? And on the previous screen, we looked at all three of those cases. Once you know that, determine the direction of the induced magnetic field to oppose that change. We did all three of these examples, so we have a summary now. If there's a steady flux, in other words, you're not changing it at all, well then, by definition, if you're not changing the magnetic field or the flux, then there's no induced magnetic field. There's no current in the wire, no magnetic field produced. If your flux is increasing, remember we're trying to oppose that change, so you need to have an induced magnetic field that points in the opposite direction. All right, so to oppose an increase, you need something in the opposite direction. Or it could be a decreasing flux. If the amount of field passing through your loop is decreasing, we need to oppose that decrease, so the induced magnetic field points in the same direction to oppose the decrease as the applied magnetic field. Once you know what direction your magnetic field is pointing, you can determine the direction of the induced current by using the right-hand rule as we discussed on the previous slide. So I know this is probably a little intimidating to begin with. It wasn't, not like it was bad enough having to deal with the right-hand rules and a current and a magnetic field. Well, now there's two currents or two magnetic fields and all the right-hand rules, and it gets crazy. So definitely practice this stuff as much as you possibly can. And to go along with that, I have 3, I believe, quick check questions and an example to help us kind of recap everything. So let's jump right into this. So keep all of this in mind going forward with our quick checks. Here's the first one. The bar magnet is pushed toward the center of the wire loop. Which of these options is true? Okay. In this case, we are moving it toward the loop, which means the flux will be increasing. right? So we are increasing the strength of the field because we're pushing it closer. So the flux will increase. In order to oppose an increase, we need to have a field pointing in the opposite direction. In other words, downward. So our induced magnetic field points downward through the loop. So by the right-hand rule, that means we will have a clockwise current in the loop. And again, this is really hard to, teach really without physically being in front of my students, because it's a lot easier to actually hold up our right hands together, trace them along these paths, things like that. I wonder if I can find like an animation of a hand or something and drag it along these paths. But anyway, so you'll get a clockwise induced current in the loop. Let's try another one. This one's a little bit different from all the others we've seen. This is actually a three-parter. So you're given three different situations. Each of them has an answer of one of the three below. So the question says, a magnetic field goes through a loop of wire as shown. If the magnitude of the magnetic field is one of those options, what can we say about the current in the loop? So you're going to have a letter answer for each of these numbers. So what happens when the field is increasing, what happens when it's decreasing, and what happens when it's constant. I'll give you a few minutes to think about it, you should pause and think about it for a few minutes and then return. Okay, well, the answers are shown now in like a light purple font. So if the magnitude of the field is increasing, okay, so here we have a field pointing into the loop. And if it's increasing, we need to oppose that increase. So we need a field in the opposite direction, which means out of the loop. If you have a field coming out of the loop, use your right hand rule, your fingers wrap around, coming out of the screen in the center of the loop, that means your thumb will point in a counterclockwise direction. The opposite is true if it is decreasing. Here we have a field going into the loop, and it's decreasing. So if that's the case, we need to oppose that decrease by also having a magnetic field in that same direction into the screen. If we have a field going into the screen by the right-hand rule, that gives us a clockwise current. And of course, if the magnetic field is constant, not changing at all, there is no change in flux, and so as a result, there is no induced current at all. So the option there is C. All right, one more. Here we have a new diagram. It says the magnetic field is confined to the region inside the dashed lines. It is 0 on the outside. The metal loop is being pulled out of that magnetic field. So which is true out of the following? All right, so this adds in one tiny extra step in our mental process. So we are taking a loop and pulling it out of a magnetic field. So ask yourself, is the flux increasing, decreasing, or staying the same? Your answer should be that it's a decreasing flux. You are taking it out of the field, so there's less flux through your loop. So it's decreasing. In order to oppose a decrease, we need a field pointing in the same direction, so also into the screen. So from the right-hand rule, if your fingers are pointing into the page at the center of the loop, your thumb then points in a clockwise direction. I forgot to underline it, but the answer here is A. It is a clockwise current in the loop. All right, one more. This time it's going to be an example though, so I'll actually work this one out with you. So here this says a loop is moved toward a current carrying wire. As it is moving, is there a clockwise current around the loop, a counterclockwise current, or is there no current? So let's go ahead and figure this out. We'll follow our LENZ'S law steps. First of all, we have one additional step before we can even really apply LENZ'S law. Let's look at this wire. We have a current moving from right to left. Using our right-hand rule, our thumb pointing in the direction of current, our fingers should be curling into the screen everywhere above the wire. I'm just randomly placing these X's But everywhere above the wire, we have a field that points into the screen. On the other side, there's not much space, but it's coming out of the screen. So you can draw a bunch of dots. That's not a dot. I don't know why it's not recognizing this. But you have a magnetic field coming out of the screen down here. All right, so that's by the right-hand rule. So, looking at what's going on, recognize that we are taking this loop and moving it closer to the source of the magnetic field. As a result, it should be getting stronger. So technically I could show that by adding even more x's here to indicate a stronger field. So we're moving it into a region that has more field. If that's the case, the flux will increase. If we want to oppose an increasing flux, we need to have an induced magnetic field pointing in the opposite direction. In other words, out of the screen. If that's the case, by the right-hand rule, if we have a field coming out of the screen in this loop, that means we should have a current moving in a sort of counterclockwise direction. And so I summarized that with an image on the bottom. So everything I've just said is kind of summarized here, and it looks pretty similar to what I've drawn. But anyway, to recap, we're moving it into a region of a stronger magnetic field. So as a result, the flux into the loop, or through the loop, is increasing. To oppose that increasing change, we need to have a field in the opposite direction, which would be out of the page. By the right-hand rule then, if you have a magnetic field pointing out of the page, your thumb will point in a counterclockwise direction, and thus we have an answer. So I hope with all these examples it helps to clarify a little bit about how Lenz's law works. From here, we've got just another lecture or two on this material before we conclude. As always, thanks for watching and have a great day.